So in problem number 2, it's just a pi operator starting at I equals 1 to I equals 3. This isn't a combination or a permutation problem. It's just familiarity with using the pi operation. So when I equals 1, you're going to have 1 times 2. When I equals 2, you're going to have 2 times 3. And when I equals 4, when I equals 3, you're going to have 3 times 4. And what you're going to do with all these is just multiply each of these up together. And what do we end up getting? Let's see, 4 times 9, 36 times 4, 144. In the third problem, now this is falling into a combination problem, because if we were to expand, general expression is 7 minus I over 5 minus I, and if I were to expand this, I would get 7/5 times 6/4 times 5/3 times 4/2 times 3/1. And what we see is this is equivalent to 7 factorial over 5 factorial times 2 factorial. So this problem is the same thing as just there being 7 things and we're choosing 5 of them. So what's the actual answer? Well, this is one way of writing the answer, this is another way of writing the answer, this is another way of writing the answer, or you could go and multiply everything together, but multiplying everything together, the 5, 4, and the 3 cancel off, 5, 4, and the 3 cancel off. 6 over 2 just becomes 3, and so this just simplifies to 21. That would be like the simplified answer, but I also wanted you to see that we could write it like that. Okay, in number 4, we've got I equals 0 to 2, and we've got 12 minus I. So here, we've just got 12 times 11 times 10, stop, and what does this equal? 131, 133. Sorry, so that should equal 1,320. And this is equivalent to there being 12 things, and the order matters, permutation, and we're choosing 3 of them. Alright, in 5, what we can realize is that you can write 82 factorial as 82 times 81 times 80 times 79 factorial all over 79 factorial times 3 factorial. And so those go away. And then we could simplify this. This simplifies to, well, I'm not going to multiply this out. You can do this on a calculator. That should have been 80 all over 6. And this is a combination problem. And it's a combination problem where you could either think of it as 82 things choose 79, which is equivalent to 82 things choose 3. In the 6th problem, we've got 103 factorial over 100 factorial, which is just 103 times 102 times 101 times 100 factorial over 100 factorial. 100 factorials go away, So we just have these three terms. Whatever this equals. You could use a calculator to generate an answer for this. What type of problem is this? This is 103 things, and we want to see how many different ways we can arrange them when order matters if we were to choose 100. Okay, and the seventh problem, there's a bunch of different problems for these. So we've got 9p3, which we can write as 9 factorial over 6 factorial, which we could also write as, let's see, this would simplify to 9 times 8 times 7 times 6 factorial over 6 factorial. We could also write it as the product from I equals 0. Well, we have three terms, so to I equals 2 of 9 minus I. Yeah, good. Okay, so that was 7a. 7b, we've got 12p10, which we can write as 12 factorial over 2 factorial. And this simplifies, well, 12 times 11 times 10 times all the way to 3. And you can multiply that all out. You could also write it in pi notation. This would be, since there are 10 terms, we start at our 0th term and we go to our 9th term, and we're going to have 12 minus I. In 7c, another permutation problem, almost identical. We're going to have 8 factorial over 5 factorial, which gets us to 8 times 7 times 6. We've got the three factors and they're descending. We could write this in pi notation, which is I equals 0 to I equals 2 of 8 minus I. So pi notation, factorial notation, and then simplifying. In 7d, we've got a combination. So this would be 9 factorial over 6 factorial times 3 factorial. And again, the effect of this 3 factorial is just to divide away all of the duplicates. So this would be 9 times 8 times 7 times 6 factorial over 6 factorial times 3 factorial. That goes away. And then this will simplify. 3 factorial gets rid of one of the 3's here and then one of the 2's there. And then we have, 21 times 4, 84, I think. And written as a pi notation, we'd have, starting at I equals 0, going up to I equals 2, we're going to have 9 minus I, which will give me the 9 times 8 times 7, and then over, say, 3 minus I, which is going to give me the 3 factorial. In E, we've got another combination, 7e, we've got 12 combined with 10, so we have 12 factorial over 2 factorial times 10 factorial. And this will simplify to 12 times 11 times 10 factorial over 2 factorial times 10 factorial. So the 10 factorials go away. That simplifies to 6. We get 66. We could also write this in pi notation. We start at our first factor. We've got 10 of them, so we're going to go to I equals 9. And then we have 12 minus I over 10 minus I. And our last problem, 7f, we've got 8 things combined 3 ways where order doesn't matter. So we've got 8 factorial over 5 factorial times 3 factorial, which is 8 times 7 times 6 times 5 factorial over 5 factorial times 3 factorial. 5 factorials go away, 6 cancels out with 3 factorial, we're left with 56. Written in pi notation, we have pi I equals 0 to I equals 2, 8 minus I over 3 minus I. So we're just looking at different ways in which we can express the same idea. In problem number 8, we've got a telephone number with 10 digits. Each digit, there are 10 digits to use. In part G, I don't know, well, in the first part, when there's unique phone numbers, maybe this could have been clearer. So if numbers can be repeated, there are 10 spots and 10 possible options for each spot. So if numbers can be repeated, we're just talking about 10 to the 10th. However, if numbers can't be repeated, then we're going to have 10 digits from which we're choosing 10 of them. So that's just going to be 10 factorial. And for C, if you use 8 at least once, I'm going to use the next page for that. So let's just, since the question says use the 8 at least once, we're going to assume you can repeat numbers. So the idea here, if we're talking about at least 1 8, let's find number of ways for no 8. Well, the number of ways for no 8 would be 10 spots, and for each spot you're choosing a digit that isn't 8. So how many digits can you choose? 9 digits. So this would just be 9 times 9 times 9, 10 times, or 9 to the 10th. So that's all. This is all the ways that you get no 8s, and 10 to the 10th are all the ways that you can get any combination. So any combination minus the combination where you get no 8s is going to equal number of ways for at least 1 8. Okay, in 9, we've got 8 blue stickers and 5 orange stickers and 4 pink stickers. And if we're going to put all these stickies in a line, how many unique combinations are there? Well, in total, we've got 17 stickies. So if the color didn't matter, it would just be 17 of my objects and order them in 17 spots, which is 17 factorial. But then we need to get rid of the redundancies that happen from, if it's a blue, whether, there are 8 blues out there, and the order of those blues won't make a difference. We can't distinguish between the blues, so we're going to divide away by all the different ways that you could arrange, once we've set out the colors, all the different ways that you could rearrange the blues, and then rearrange the oranges, and then rearrange the pinks, so that we get rid of their redundancies. So, once we've arranged them, there are 8 ways in which we could order the 8 blues, and 5 ways we could order the 5 oranges, and 4 ways we could arrange the 4 pinks. That would give us the exact same results, just switching the placement of them. So we could simplify this as 17 factorial over 8 factorial times 5 factorial times 4 factorial. in 10, we've got 12 chairs and 16 students. So in the first part, it says how many different groupings where all the seats be filled are there if order does not matter. Well, so that we've got 16 students and we are choosing 12 because order doesn't matter. So we have 16 times 15 times 14 times 13 times 12 factorial all over 12 factorial times 4 factorial. And so this will simplify out a little bit. 4 factorial we can write as 4 times 3 times 2. So this simplifies to 4, the 3 simplifies to 5, the 2 here simplifies to 7. And so this will be 4 times 5 times 7 times 13, whatever that is. In the second part it says, okay, how many different groupings of students where all seats will be filled are there if order does matter? So now order matters, so we've got 12 permutation, or 16 permutation 12. So we've got 16 factorial over 4 factorial. And this is the way in which order does matter. But what we need to do is think about a circle. So let's just think about a circle of maybe 5 spots. So imagine this is our circle. And what we need to do here is distinguish like whether the seat matters or the order matters. One could make the argument that this question is ambiguous because you could have like A, B, C, D, E around the circle, or you could have A, B, C, D, E around the circle. And for those in the circle, once you're sitting in the circle, these orientations wouldn't matter because your reference point, you're still seeing the same people in the same spots. So this is the answer if the seat matters. But if the seat doesn't matter, if all we care about is if order matters, we need to divide away all the different ways, all the different iterations that are the same people just shifting over a seat. So we'd have 16 factorial over 4 factorial, and then we're just going to divide that by 12 because there are 12 different orientations of that seat that will, because there are 12 chairs, we could just rotate 12 times and be in different places. This is a potentially tricky idea to understand, but take some time to think about that. Alright, so in 11 we have 3 boys and 4 girls being selected to a committee. So each of the classes is different. So let's just say that there are 10 boys and 10 girls. This isn't true in our classes. But if we were going to do this, we're choosing 3 boys from 10 of them, and the order doesn't matter. So that's one of our events. And then the second event is choosing from 10 girls, choosing choosing 4 girls. So let's say again what we have here. Here we had, whoa, that's not what I wanted to do. Yeah, we had 10 boys and we're choosing 3. That's our first event. And then we multiply by having 10 girls and choosing 4. This would simplify a little bit. I'm not going to go the whole way, but 10 factorial over 7 factorial times 3 factorial times 10 factorial over 6 factorial times 4 factorial. And you can go ahead and simplify that if you will. In 12, I'm choosing from a deck of 52 cards, I'm choosing 5 of them. And all we care about is what 5 cards come to our hand, so the order does not matter. So the idea is we get dealt 5 cards, and whatever order in which they came to us, all we care about is what are the 5 cards that we have. So we select 5 from 52. In 13, we're taking 5 cards from 52, but it says how many ways can I get 5 hearts? So if you're getting 5 hearts, what that means is, if you think about cards, we have 13 spades and 13, let's see, clubs, and 13 hearts, and 13 diamonds. Well, if I'm only getting 5 cards and I want to know how many ways I can get 5 hearts, all of my cards must be coming from the hearts pile. So really I'm just saying there are 13 hearts from which I can choose 5 of them. And so that's how many ways I can get 5 hearts. Again, this would be 13 factorial over 8 factorial times 5 factorial. Okay, the last one I'll do, the challenge ones I'll leave for you to figure out. It says how many ways can I get 5 hearts or 5 diamonds or 5 clubs or 5 spades, which is called a flush. Well, using the problem from before, for me to get 5 hearts, I showed that it would be 13C4. Now, whether it's going to be the same logic for getting 5 diamonds or getting 5 clubs, it's going to be the same thing, or getting 5 spades. So since there are 4 ways to get 5 hearts or 5 diamonds or 5 clubs or 5 spades. In other words, there are 4 ways to get. Oh, this should be a 5. Since there are 4 ways for me to get 5 of one suit, it's just 4 times 13 choose 5, which is 4 times 13 factorial over 8 factorial times 5 factorial.